Good morning, ladies and gentlemen. Welcome to heat transfer lesson number 39. Today is a continuation of last time's lesson, number 38, where we looked at exchange between gray bodies. So with that as an introduction, last time, if you recall, we looked at the exchange of radiation between two bodies that were gray and diffuse. This time, we're going to look at three bodies. So without further ado, let's begin. Let's take and begin by looking at some examples of three-body enclosures. And their electrical networks. There are several different examples of types of three-body enclosures. One, which is quite common, is the triangular enclosure. This might be some sort of channel for flow of wires or something of this nature, where we have A1, we have T1, and we have epsilon 1. We have A2, T2, and epsilon 2, and we're talking now about the inside of these surfaces. And A3, T3, and epsilon 3. That might be one type of three-body enclosure. We also have enclosures that look at this nature. You say, well, that's not a three-body enclosure. That is in fact a six-body enclosure. But what we can do is we can arrange this so that we have, for example, this could be the top, could be A1, T1, and epsilon 1. The bottom could be A2, T2, and epsilon 2. And then we could just group all three sides together, and the sides could be A3, T3, and epsilon 3. So by being creative, we can come up with different ways of reducing a problem which might look more complicated on its surface to a three-body problem. Now the question is, what does the electrical network look like? I've misspelled electrical. There we are. What does the electrical network look like? Well, you're familiar with this from circuits, so let me draw it. Now, we'll go ahead and label this, and recall that we had our resistances, our spatial resistances and our surface resistances from last time. So we'll label this EB1, and then we'll have the surface resistance, which would be 1 minus epsilon 1 over epsilon 1 A1, and this would be J1, our reciprocity, our radiosity at this first node here. And the heat transfer which would be occurring would be Q1. Okay? This would be Q1. Then this would be the black body emissive power at 2 over its surface resistance, 1 minus epsilon 2 A2, and this would be the radiosity at 2. And this would be Q2. Now, down here we would have the emissive power, black body power at 3. This would be, node would be J3, and this would be 1, this resistance, the surface resistance would be 1 minus epsilon 3 over epsilon 3 A3. Just as we learned in last time's class. Oh, and let me not forget, this would be Q3. Then we have the shape factor. How does the one surface see the other surface? So how does surface 1 see surface 2? And this can be expressed as 1 over A1 F1 to 2, or if you'll call from reciprocity, this could just as well be 1 over A2 F2 to 1. And this would be the heat transfer Q to 1, Q1 to 2. Q1 to 2. This would be the shape factor 1 over A1 F1 to 3, or it could just as well be 1 over A3 F3 to 1. And this would be Q1 to 3. And this could be 1 over A2 F2 to 3, or 1 over A3 F3 to 2. And this would be Q2 to 3. So now we have our circuit labeled with all of our nodes, EV1, 2, and 3, J1, J2, and 3, the surface and or the shape factors, resistances for how these sides, how these surfaces see each other, and we've also labeled all of the heat transfers that take place. All right, now, from last time's class, you can gather this for the heat transfer from surface 1. We have Q1, which would be equal to EB1 minus J1 over 1 minus epsilon 1 over epsilon 1 A1. All right? The problem is that's a bit of a problem, and that's one of the problems we're going to solve today. So we have to look at other equations. So we must look at other equations with the radiosities J. And what we're going to do is we're going to come up with a series of equations, and let me show you what these are going to look like. What we're going to do is we're going to take and write the nodal equations for these three nodes. This node here, this node here, and this node here. All right? So let's do that. We have three unknowns. And these unknowns are J1, J2, and J3. Our three radiosities are unknown. Now in some cases we may be able to solve for the radiosity if we know the irradiation and we know the temperature of the surface, but let's assume for the time being that we don't. So let's look at node number 1 to begin with. Now, I'm going to write my equations so that the energy balances. In other words, what comes into the node is equal to what leaves the node. Now, my choice of directions of the heat transfer are completely arbitrary. As we solve the problem, if we turn out with a heat transfer that is negative, that simply means that the heat transfer is going in the direction opposite to what we assumed. All right? So let's look at node number 1, which is around J1. And in that case, we have Q1 in, and leaving we have, we have Q1 in, and leaving we have Q1 to 2 plus Q1 to 3. And now we're going to express this in terms of the equations like we did over here. So for Q1, we'll have EB1 minus J1 over 1 minus epsilon 1 over epsilon 1 A1. And that must be equal to Q from 1 to 2. And the nodes there are J1 minus J2 over 1 over A1 F1 to 2 plus heat transfer from 1 to 3, which is J1 minus J3 over 1 over A1 F1 to 3. Now, you'll notice in this equation, we have emissive property, which should be known. We have the areas, which are known. We have these shape factors, which we should be able, from our previous experience, to ascertain. And we have EB1, which of course is sigma times T1 to the fourth power. And then we have the 3 unknowns, J1, 2, and 3. So now I'm going to write the equation for node number 2. Now look at your notes, because in node number 2, we have, coming into node number 2, we have Q2, and we also have Q1 to 2, and leaving we have Q2 to 3. So our equation will look like this. Q2 plus Q1 to 2 is going to be equal to what leaves, which is Q2 to 3. Putting it in these terms, Q2 would be EB2 minus J2 over 1 minus epsilon 2 over epsilon 2 A2 plus Q1 to 2, which would be J2 minus J1, J1 coming in. No, that would be it would be J1 to 2 over, let me double check. I don't want to, yes, that's correct. J1 to minus 2 over 1 over A1 F1 to 2, and that would be equal to J2 minus J3 over 1 over A1, 1 over A2 F2 to 3. Once again, note what we have. We have an emissive, black body emissive power, that's sigma times T2 to the 4th power. We have the properties of the material E2, or epsilon 2, the emissivity. We have the areas, and we have the shape factors. So all the thing we don't know in here are the 3 radiosities. Okay? So now, we do node number 3. Okay? Node number 3, if you look at your notes, you'll see we have all 3 heat transfers going into J3. So that means everything in must be equal to 0. So that would be EB3 minus J3 over 1 minus epsilon 3 over epsilon 3 A3 plus J1 to J3 over 1 over A1 F1 to 3 plus J2 minus J3 over 1 over A2 F2 to 3, and these would be equal to 0. All right, once again, same result. An emissive black body power, material properties, areas, and shape factors. So what does this all boil down to? At the end of the day, these are all numbers except for J1, J2, and J3. You have 3 equations with 3 unknowns, and so you can substitute and solve for your unknown J's. All right, so 3 equations, 3 unknowns. You can solve by substituting. Or using a series of linear equations, using linear algebra. The net result is you can solve this problem. And once you know these radiosities, then it's relatively easy to solve for the heat transfers. Let's talk a moment about the different, some very different special cases which apply and which make our life a little bit easier when it comes to 3 networks, when it comes to radiation exchange networks of 3 or more bodies. The first special case is a very large surface. An example of a very large surface is the sky. It's a great example of a large surface. In which case, in that case, the area is very, very large. If that is the case, we look at the network. Where you have EB1 and you have J1. And you have 1 minus epsilon 1 over epsilon 1 A1. If A is very, very large, then this resistance is what? It's very, very small. So in that case, J1 is approximately equal to EB1, which means it's equal to sigma times T to the 4th. That's the case for a very large area. Okay? You don't need to worry about making a judgment call in this course on what is a very large area. If we're going to have you use this simplification, this special case, we'll say that you can treat area, whatever, as a very large area. Okay? The second is where we're dealing with a black body. If we're dealing with a black body, epsilon is equal to 1. In other words, we have a perfect emitter. So in that case, we have 1 minus 1, and again, the resistance is 0, and therefore the radiosity is equal to the emissive black power. So E, B, let me write the other way, J1 is equal to EB1. And that again is equal to sigma times T to the fourth. The last special case which we're going to be dealing with is an adiabatic, or what is known in the trade as a re-radiating surface. Okay, an adiabatic or re-radiating surface. In other words, the net heat transfer is equal to 0. Okay? So we take the surface, like so. We still have G coming in. We have a certain amount of G which is reflected, that is the reflectivity times the irradiation, G. And of course we have the emissive power, which will be represented as epsilon, the emissivity times the black body emissive power. In this case, there is no the net heat transfer is equal to 0. In other words, as far as the surface is concerned, everything that comes in leaves, there's no net change in the surface. All right, so it's adiabatic. Now, let's do the first one. We'll start off with the first law that we started the course with. That is that energy rate in must equal the energy rate out. The energy rate in is G, and that's going to be equal to plus Q, and that's going to be equal to 0 because it's already said it's adiabatic, plus rho times G, which leaves, plus the emissivity times the black body emissive power. We'll rearrange this, bring this over here, and we'll have 1 minus rho times G is equal to the emissivity times the black body power. And this is equal to epsilon, 1 minus rho. And so we have G, the irradiation being equal to EB, which then would be equal to J, given our definition for radiosity, which is G minus E sub B would be equal to our radiosity. So in that case, J would be equal to the black body emissive power, which is equal to sigma times T to the fourth. So in each case, we end up with the same result. The net result of these, if you can scan over and catch the first board again, is that for the, let's say, the bottom of that diagram, if we're talking about surface 3 being the special case, the 1 minus epsilon, there's no difference between, there's not a third leg to this. There is simply one network with a parallel set of resistances in series with a single resistance. And so how do we set that up? Well, you've seen this before, so let's go ahead and do that. So we'll take the example of an adiabatic surface, one of our special cases. And we'll draw the resistance. And it'll look like this. And we'll label our nodes, EB1, J1, J2, EB2. This would be EB3, which as you know would be equal to J3. This would be 1 minus epsilon 1 over epsilon 1 A1. 1 over minus epsilon 2 over epsilon 2 A2. This would be 1 over A2 F2 to 3. This would be 1 over A1 F1 to 3. And this would be 1 over A1 F1 to 2. If we put the heat transfers in, this is Q1. This is Q1 to 2. This is Q2. This would be Q1 to 3, and this would be Q3 to 2. Now obviously, Q1 to 3 and Q3 to 2 are equal, so that's going to be one heat transfer over the 2. This is our adiabatic surface here. This could be also a very large surface, or it could be a black body. So the result is the same. So now we're going to rewrite this circuit as such. This would be EB1, this is J1, this is J2, this is EB2. Again, 1 minus epsilon 2 over epsilon 2 A2. Excuse me, not paying attention here, thinking ahead. This is 1 minus epsilon 1 over epsilon 1 A1. This is 1 minus epsilon 2 over epsilon 2 A2. And this we'll simply call our equivalent resistance. And this is just Q. And the Q is the same across all of these. Now, of course, this Q does split in this series right here. But in terms of how we have it now, this Q1 would equal Q1 to 2, which would be equal to Q2, or just Q. Where our equivalent resistance would be equal to 1 over A1 F1 to 2 plus 1 over A1 F1 to 3 plus 1 over A2 F2 to 3 over the reciprocal of that. And as I said, Q1 would be equal to Q1 to 2, which would be equal to Q2, which is just equal to a constant heat transfer between these two surfaces. That being said, what we have is this. Q would be equal to EB1 minus EB2 over 1 minus epsilon 1 over epsilon 1 A1 plus the equivalent resistance plus 1 minus epsilon 2 over epsilon 2 A2, which, of course, is sigma times T1 to the 4th minus T2 to the 4th over 1 minus epsilon 1 A1 plus plus the equivalent resistance plus 1 minus epsilon 2 over epsilon 2 A2. When you are working problems of this nature in your homework or exams, it is critical that you solve for this number. All right? You solve for this. What is 1 minus epsilon 1 over epsilon 1 times area 1? Because I'm going to solve for it, I'm going to know what it is. I want to know where you made your mistake. Similarly, I want you to solve for this. And I want you to solve for this. So I know that if you have all these values correct, and then you put the numbers in like I asked you to do when you're solving the problems, and you have the numbers correct, and you have a wrong answer, then you've made a math error. You pushed the wrong button on the calculator. And that's different from just writing down the equation and giving me an answer. Show your intermediate values in your intermediate equations. Okay, well hopefully that has answered your questions about three-body enclosures. Let's take the remaining time and let's do a quick example problem. So open your textbooks now to chapter 13, in particular to problem 1375. I'm going to sketch this out for you. So you can look at this problem in your book, and I won't write everything up here because it takes a lot of time to do it, but you can see that this is a classic triangular three-body problem where we are given some information. This is A1, and you're given a temperature of 1,000 Kelvin and an emissivity E1 of epsilon 1, of 0.33. This is surface A2, and its temperature is 700 Kelvin with an emissivity 2 of 0.5, and this is an insulated surface down here. And this surface A3 has a temperature T3, which you are asked to find, and you're told that its emissivity is 0.8. So what's the first thing you're going to do? You have temperatures known, with the exception of this one. You have the areas known. The areas, this is an isosceles triangle, and this is 1 meter. And we will assume, in this type of case, 1 meter into the board. Okay? So you've got 1 meter and 1 meter in, so that makes each area 1 square meter, which is nice and handy. Okay, so the first thing we do is we draw the triangle, or we draw the electrical circuit. We label our nodes. We label our resistances. And of course, this is exactly like the resistance which I drew 2 boards earlier. And this is our equivalent resistance. We'll get to that in a moment. And there is a Q which is passed along that line. All right. So what do we know? We know that first thing we need to do is we need to figure out some of these values. We're told epsilon 1, so we know those. I've already told you we're going to assume 1 meter into the board, so each one is 1 meter in width, and 1 meter into the board, so it's 1 square meter, so we know A1, and we know A2, and we're given epsilon 2 as well. So now we need to figure out our equivalent. Let's refresh our memory as to what our equivalent is. and it's right here. And in order to do that, we need to figure out what F1 to 2 is, what F1 to 3 is, and what F2 to 3 is. Now some of you, I suspect, have already figured this out. How does surface area 1 see surface area 2 and 3? Now, as you know from a couple of classes ago, we know that the view factors must sum to 1. In other words, there are 3 view factors that could come into play here. F1 to 1. Does surface 1 see itself? And the answer, of course, is no. It doesn't see itself because it's a flat plane. So how does surface 1 see surface 2 and surface 3? This is an isosceles triangle, so it's going to see area 2 exactly like it does area 3. So that means F1 to 2 is going to be equal to F1 to 3, which is equal to F2 to 3, and that's each going to be 0.5. So that means we can go ahead and solve for these different values. If we do that, we can come up with a value for the heat transfer, the total heat transfer, because we know temperature at 2, and we know the temperature at 1. So the heat transfer is going to be equal to sigma T1 to the 4th minus T2 to the 4th over 1 minus epsilon 1 A1 plus the equivalent resistance plus 1 minus epsilon 2 over epsilon 2 A2. You can go ahead, and all of these are regular numbers, and it turns out that this turns out to be 9,874 watts.